in section 4.1, we'll be going over the first derivative test. Let's review some topics from Algebra 2 or Pre-Calculus. So in those classes, you talked about where functions were increasing or decreasing, thinking about their different characteristics of the graph. And you might have used sign charts, look at the end behavior, all of those things. So let's write out a few definitions. So first of all, a function is increasing if f of x sub 2 is bigger than or equal to f of x sub 1 if x sub 2 is bigger than x sub 1. So that just means when I move from left to right, the y value is larger. And if the opposite of that is true, then our function is decreasing. So notice the equality there. I could have the same y values for a second, and then as long as it keeps increasing after that. If you take that equality off, then we just say it's strictly increasing and strictly decreasing. So you can see here, this is an increasing function. It is constant for a moment, but technically it's greater than or equal to the point before it, and then it continues on up. Strictly increasing would be something like x minus 1 to the third power. And so what we want to connect this to is those were pre-calculus or algebra definitions. We want to start thinking about what this means in terms of calculus. So if my function is increasing, that means I have a positive slope. And so in calculus, if we have a positive slope, then that means our derivative is positive. So what we're going to say is if f prime of x is greater than 0 for all x in an open interval a to b, then f is increasing on the closed interval a to b. So we're not really particular about the points. We don't talk about if a point is increasing or decreasing. We talk about an interval increasing or decreasing. So you'll notice we'll check to see if it's greater than 0 on an open interval, and then we can include the endpoints there. Same idea, if our derivative is negative for all x in the open interval a to b, then f is decreasing on the closed interval a to b. And lastly, if f prime of x is equal to 0, then f is constant on that interval. And so you'll see sometimes some answers will have closed intervals there, like in this definition. Sometimes they'll be open intervals or one side or the other. And so any of those answers will be acceptable on the AP exam and on Delta Math. Okay, a critical value is a value of x where f prime of x is equal to 0. So that would be a horizontal tangent line. Or f prime of x is undefined. So like a vertical tangent line, an asymptote, it could be a corner or a cusp. And so these critical values, think about the English word critical, it just means important. These are usually the first step when we're analyzing a function, and these are the places where we could have our function switch from increasing to decreasing. So in example 1, it says to find the critical values of f, and then to determine intervals of increasing or decreasing. So the first thing we want to do to find our critical values, we have this polynomial. We're going to take our derivative and we'll set it equal to 0. So our derivative is 12x minus 3x squared, and we're going to set that equal to 0. We do need to think about when f prime is undefined, but anytime we have a polynomial, it will always be defined. So in order to solve this, we're going to need to factor. We can factor 3x out of both terms. Then we would have a 4 minus x left over. And set each term equal to 0, each of the factors, and we would get x equals 0 and x equals 4. So these right here are what we call our critical values. So if it just asks for critical values, that's where we would stop. But it does ask the second part, determine intervals of increasing or decreasing. So we're using those definitions from above. If f prime is positive, then it's increasing. If f prime is negative, then f is decreasing. So what we'll have to do to determine that is we'll need to make a sign chart. And this is a sign chart for f prime. On f prime, we'll put our zeros, our critical values. So we have 0 and 4. Those are the only places my signs could change. And then we'll pick test points in between those intervals. So like -1, +1, +5. And then we'll plug in those test points into my factored form, 3x times 4 minus x. If I plug in -1 to 3x, that's negative. If I plug in -1 to 4 minus x, that's positive. So this interval would be negative. If I plug in 1 to 3x, that's positive, and into 4 minus x, also positive. So this interval is positive. And if I plug in 5, I would have a positive and then times a negative. So that means this interval is negative. So your sign chart cannot be your final answer. You'll use it to get your answer, but you will not get any points on the AP test for that. So what you're going to say is we have to write out our answer with justification. So f is increasing. I'm looking to see where my derivative is positive. And so it's positive on this interval here, so between 0 and 4. So f is increasing on the interval from 0 to 4. And our justification is since f prime is greater than 0 on the open interval 0 to 4. For decreasing, I'm looking to see where my derivative is negative. So that would be from -infinity up to 0 and 4 to positive infinity. So f is decreasing on the interval -infinity to 0, union 4 to infinity, since f prime is less than 0. Now that we've talked about where functions are increasing or decreasing, we can think about the first derivative test. So in the first derivative test, as you can imagine, we will use the first derivative. So we're assuming here c is a critical number or a critical value of the function. And if f is differentiable, then we can classify these things as follows. So if f prime changes from negative to positive, so let's think about what that means for f. If f prime is negative, that means that f is decreasing. And then if it changes to positive, my function is changing from decreasing to increasing. So decreasing, down, and then up to increasing. F of c would be a relative minimum of f. If f prime changes from positive to negative at c, so that means, again, f is changing from increasing to decreasing. So we're just thinking about the synonymous statement for f. Then f of c is a relative maximum of f. And if f prime does not change its sign at c, so you could have a critical value where the derivative does not change signs, then f is neither a relative minimum nor a maximum. It's just a regular horizontal tangent. So you can see these graphs below. Here my graph of f, I see it changing from decreasing to increasing, but we're looking at the calculus definition of f prime, the slope changing from negative to positive, and I can see that this graph has a relative minimum. The opposite is true. If I change from positive to negative on my derivative, I would have a relative maximum. In the last graph, my slope is positive, and then it stays positive after my critical point, and so that is neither a relative max nor a min. And a curve can have more than one. We would say, if we were talking about minima and maxima together, we would say extrema. And you will see both the terms relative and local. And don't get those confused with absolute maxes and mins. Those are the largest value or the smallest value on a curve within a given interval. And so when we're talking about relative maxes and mins, we're really talking about like bottoms of valleys, tops of hills, okay? Overall, absolute maximum would be like that point right here. Okay, so in our example, we want to find all of the intervals where f of x is increasing or decreasing, and the x values where it has a relative max or min. Then we're going to graph it and check to see if we get the same thing. So our first step, if it's not given to us, is to find f prime of x. So f prime is, I have to use chain rule here, 2/3 times x plus 2 to the negative 1/3. And the derivative of plus 1 is just 0. And then you will want to rewrite it if you can without that negative exponent. So this would be 2/3 cube root of x plus 2. Your second step after that is to find your critical values. So that's where we set f prime equal to 0 or undefined. When I look at my f prime here, to determine where it's 0, I would look at the numerator, 2, that's never equal to 0. To see where it's undefined, I would look and see where the denominator is 0. And so I can really zoom in on this x plus 2. That would be 0 when x is negative 2. So my critical value is at x equals negative 2, since f prime would be undefined there. So I would be dividing by 0. You don't do this any differently when f prime is defined versus undefined. After I found my critical values, then it's time for us to make our sign chart. And this is a sign chart for f prime, remember, so we're going to use our derivative here. My x value is negative 2. I like to leave that open so I remember that it's undefined, but you can mark it however you want on your sign chart. A number to the left is negative 3. A number to the right is negative 1. So if I evaluate this at negative 3, if I plug that into my derivative, I would get something that's negative. If I plug in negative 1, I would get something that is positive. And now you need to give your answers with justifications. So if you give answers and you don't justify them, you would get 0 points on the AP test and on tests in our class. All right, so first let's say f is decreasing. It asks me for me to find intervals of increasing or decreasing. So I see it's decreasing here up to negative 2. Now this is my first derivative is undefined, but my actual function is defined, and so I can use a bracket here. F is decreasing on the interval negative infinity to negative 2 included, since f prime is less than 0. F is increasing. I'm going to be looking to see where my derivative is positive. So on that whole interval, from negative 2 to infinity, since f prime is greater than 0. The last thing we need to do is find if we have a relative max or a relative min. So in order to do that, we are paying attention to the sign change here. I'm going from negative to positive. So negative means I was decreasing, positive means I'm increasing. That will be a relative minimum. So f has a relative minimum. And I cannot say it has a relative minimum because f changes from decreasing to increasing, because that is a pre-calculus definition. We have to use calculus. So f has a relative minimum at x equals negative 2. These will be your critical values. And our justification is since f prime, we have to talk about the derivative. This is calculus, so we talk about the derivative. Since f prime changes from negative to positive. Okay, let's go ahead and sketch our graph here. You could use a calculator or Desmos to graph this. What this is, you can maybe tell here this would have like a vertex point of negative 2, 1, if you think about like shifting over a parent function. And what this graph looks like when you have a graph to the 2/3 is, I call it a bird graph. Sorry, my point keeps disappearing. And so it's kind of like x cubed, but one part is flipped up. And so there's a point here, another point over this way. So it's just kind of like a curvy, I call it again a bird graph. It looks like one of those birds you would draw in kindergarten. And you can see here, this isn't the best drawing, sorry, it has a cusp. And that's why our derivative was undefined. But I can see here that it was decreasing on this interval to the left of negative 2, increasing to the right of negative 2, and it did have a relative minimum at negative 2.